Now the next topic, that is power in LCR series AC circuit. Now see, we have the equation of supply voltage, that is Vm sine omega t, and current in the circuit at any instant, that is Im sine omega t plus phi, that we already discussed. Now in this equation of current, this Im, that is Vm upon under root R square plus Xc minus XL square, and this phase difference phi that we can calculate by the equation tan inverse Xc minus XL by R. So instantaneous power, that we can write V into I. Here voltage, that is also instantaneous, current, that is also instantaneous. So we can write V into I, that is instantaneous power. So V, that is Vm sine omega t, I, that is Im sine omega t plus phi. Now here multiply and divide by 2. So we can write Vm Im by 2 into 2 sine omega t plus phi. So 2ss, 2 sine. So for that, in trigonometry, you have the equation. As per that equation, here directly, this 2 sine omega t plus 5, that identity is written as cos 5 minus cos 2 omega t plus 5. Now, this one is the equation for instantaneous power, power at any instant t. But now if you want to calculate average power over one cycle, then we have to take average of this bracketed term. So average power, that is Vm Im by 2, that is constant part. So average of cos 5 minus cos 2 omega t plus 5. But this cos 5, that is also constant one in this bracketed term. So average power, that is Vm Im by 2 cos 5 minus average of cos 2 omega t plus 5. But average of cos 2 omega t plus 5 over one period, that is 0. So we can write average power, that is Vm Im by 2 cos 5. So we can divide these two in two part, root 2 into root 2, and Vm by root 2, that is Vrms. So we can say that is RMS voltage, and Im by root 2, that is RMS current. So now simply we can write the equation of average power, that is equal to Vi cos 5, where cos 5, that is called power factor. That is called power factor. Clear to all of you? So this one is the theory of. Now the equation of average power P, that is equal to Vi cos 5, where cos 5, that is called power factor. Means here we can observe this thing in LCR series AC circuit. Power not only depends on voltage and current, but it also depends on the phase difference between voltage and current. Phase difference between voltage and current. Okay. Now see here. Suppose the circuit is only the resistive circuit. It implies that inductor and capacitor are not connected in the circuit. So in that particular case, the phase difference between voltage and current, that is 0. So cos 0, that will be equal to 1. So in that particular case, the power dissipation, that will be maximum 1. But suppose we think about only capacitive or inductive circuit. So in that particular case, what happens? The phase difference, that is plus or minus pi by 2. So in that case, cos pi by 2, that is 0. So power dissipation will be 0. No doubt, current will be there in the circuit. But then also the power dissipation will be 0. So when the current is flowing in the circuit and power dissipation is 0, that particular current is called wattless current. That is called wattless current. Clear to all of you? And therefore, we use inductor or resistor to minimize the dissipation of power. And in case of LCR series circuit, in LCR series circuit, this 5 that we can calculate by tan inverse XC minus XL by R, and then depending on the value of this phase difference 5, we will get the dissipation of power. Clear? And when the resonance takes place in the circuit, so when resonance takes place at that time, XC equal to XL. So in that case, again here, phi that will be equal to 0. And when phi is 0, cos 0 is 1. So power dissipation will be maximum 1. And that is V into I, or we can write I square Z. But in this case, Z equal to R. So we can write simply I square R also. So in this way, due to which component in the circuit, how the power dissipation takes place, that we can understand. So if power factor is high, then the power loss that will be minimized. બરોબર છે? એટલે એક issue થાય. Then after B, power factor can often be improved by the use of a capacitor of appropriate capacitance in the circuit. Explain. Now see, that can be understood with the help of this particular graph. See, there is the phase difference between voltage and current, that is phi. Suppose we take this one is the voltage phasor, this one is the current, and the phase difference between voltage and current, that is phi. So now we can take two component of current. One is IP, another one is IQ. Okay. Now see here, this IQ, that is called wattless current, because that is perpendicular to voltage. And perpendicular to voltage hoy, તો voltage current એટલે particular IQ current જે છે એના માટે phase difference pi by 2 થઈ જાય. તો એનાથી power dissipation minimize or 0 થઈ જશે. એટલે આ wattless current થયો આપણો. Right? હવે આપણને શું કહ્યું છે એમણે? So power factor can often be improved by the use of the capacitor of appropriate capacitance. હવે power factor ને તમારે improve કરવો છે. Improve કરવો છે means કે you want to increase the power factor. તો increase કરીને કેટલો increase કરી શકો? તો power factor એટલે cos ની maximum possible value, that is 1. If you want to increase the power factor up to 1, then you have to make phi equal to 0. હવે આ જે ગ્રાફ છે એમાં તમને સમજ પડે કે જો આ phi ને તમારે 0 બનાવવું હોય તો તમારો કરંટ જે છે that should be only along V. તો તમારો phi 0 આવે. પણ હવે અત્યારે સિચ્યુએશન શું છે આપણી કે કરંટ અહીંયા છે એટલે એના બે કોમ્પોનન્ટ મળે છે, this IQ that give you the wattless current. તો હવે આપણે એક કામ કરીએ કે કેપેસિટર જોઈન કરીએ સર્કિટમાં. Now capacitor, for that current lead the voltage in phase equal to pi by 2. So if we connect the capacitor in the circuit, તો હવે કરંટ જે છે એ વોલ્ટેજ ને લીડ કરે એવો એક મળશે તમને અહીંયા. તો અહીંયા જો તમને આ કરંટ મળ્યો કે જે વોલ્ટેજ થી પાઈ બાય 2 આગળ બતાવ્યો આપણે, તો that is exactly opposite to iq. તો હવે સિચ્યુએશન શું થાય કે this current and this current both are opposite અને મેગ્નિટ્યુડ વાઇઝ ઇક્વલ આવશે, કારણ કે કેપેસિટરનો કરંટ બી જે છે વોટલેસ કરંટ હોય ઓલવેઝ. તો આ પોર્શન કેન્સલ થઈ જાય, મીન્સ યુ વિલ ગેટ ઓનલી ધીસ કરંટ, અને આ એકલો કરંટ આવ્યો that is in the direction of voltage, મતલબ કે phi તમારો 0 થઈ ગયો. So in this way you can improve the power factor, કારણ કે પાવર ફેક્ટર જો તમે મેક્સિમમ રાખો તો રિક્વાયર્ડ પાવર માટે તમારો કરંટ કંટ્રોલ્ડ રહે. જો પાવર ફેક્ટર તમારો ઘટી જાય, એટલે જો તમે ફેઝમાં વોલ્ટેજ અને કરંટ ના રાખ્યા હોય તો તમારો પાવર લોસ આવે, એટલે તમારે કરંટ એ વખતે રિક્વાયર્ડ પાવર માટે વધારવો પડે, અને જો કરંટ વધારો તો I²R પ્રમાણે ડિસિપેશન ચાલુ થઈ જાય તરત જ, એટલે લોસ વધવા માંડે ઇમિડિયેટ. Chalo, clear to all of you? Example 7.8. A sinusoidal voltage of peak value 283 volt. Here it is specifically mentioned this is peak value. Be careful. Okay. And frequency 50 Hz is applied to a series LCR circuit in which R is 3 ohm, L is 25.48 millihenry, and C that is 796 microfarad. Find A, the impedance of the circuit, B, the phase difference between the voltage across the source and the current, C, the power dissipated in the circuit, and D, the power factor. Simple thing. Peak voltage that is 283 volt, frequency that is 50 Hz, resistance 3 ohm, inductor with inductance 25.38 millihenry, so into 10 raised to minus 3 Henry, capacitance of the capacitor that is 796 microfarad, that is 796 into 10 raised to minus 6 farad. Now impedance of the circuit, so that is Z equal to under root R square plus XC minus XL whole square. So first of all we have to calculate XC and XL. So XC that is 1 upon 2 pi FC. Substitute all the values, 2 pi 3.14 F50 C 796 into 10 raised to minus 6, you will get XC. Then XL 2 pi FL. So 2 pi 3.14 F50 L 25.38 into 10 raised to minus 3, you will get this one. Clear? Then after Z, so Z that is under root R square, R that is 3 square of it. Then after XL, XC we already calculated. So here XL minus XC, whatever is the value that we have to substitute, and then after solve it, you will get answer of Z. Then after we want to find question B, the phase difference between voltage across the source and the current. So phi that is tan inverse XC minus XL by R. XC, XL are calculated here. R that is given to you 3. Substitute and then find out this ratio XC minus XL by R. And then after from the table of natural tangent, Find out the value of phi. Then power factor. Power factor means cos phi. So cos phi, that is equal to adjacent upon hypotenuse. So adjacent, that is R, hypotenuse, that is Z. So by taking R by Z, you can calculate cos phi. So that is power factor. Cos 5 આખો ગણવાનો છે 5 માં પછી કઈ લેવા દેવા નથી એમાં. જ્યારે જ્યારે પાવર ફેક્ટર કે ને ત્યારે cos 5 આખું ગણવાનું, 5 ને છૂટો નહીં પાડવાનો, કારણ કે cos 5, that term is called power factor. Phi itself is the phase difference. Okay, એટલે ધ્યાન રાખવાનું. Then power. So power P, that is V into I into cos 5. Cos 5 is calculated here. But voltage, so peak voltage is given to you. So RMS voltage, that is peak voltage upon root 2. So 283 by root 2 you will get RMS voltage. Once we have RMS voltage, then RMS current, that is RMS voltage by Z. RMS voltage is calculated here and Z, that is calculated here. Substitute the values, you will get RMS current. Now substitute here RMS voltage, RMS current, and the value of cos 5, you will get power. Clear to all of you? Example 7.9. Suppose the frequency of the source in the previous example can be varied. What is the frequency of the source at which the resonance occurs? Calculate the impedance, the current, and the power dissipated at the resonant condition. So resonant frequency omega 0, that is 1 upon root LC. As per that we can write 2 pi f0, that is 1 upon root LC. So resonant frequency f0, that is 1 upon 2 pi root LC. Now here substitute all the values, the value of L and C that we have to take from the previous example, and then calculate it. You will get resonant frequency. Now at resonance, XL equal to XC. So in that particular case, Z equal to R, and value of R, that is given to you 3. So you will get Z equal to R equal to 3. So now at resonance, the power dissipated, that is I square R, because at resonance your Z itself is R. Now we calculated Z equal to R, that is given to you, direct substitute, that is equal to 3, and value of RMS current. So RMS current, that is RMS voltage by Z, but Z equal to R. So you can rewrite this one RMS current, that is RMS voltage by R, but RMS voltage, that is not given to you directly. So you can write RMS voltage, that is peak voltage by root 2. So now finally you can write I, that is Vm by root 2R. So substitute here the value of Vm from the previous example, R, that is 3 from the previous example, and calculate I, and then you can calculate power P, that is I square R. Clear to all of you? Now 7.10, example 7.10, that is pure theoretical. We have to read it. At an airport, a person is made to walk through the doorway of a metal detector for security reasons. If she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does this detector work? Actually, this detector works on the principle of resonance, right? Now, see how it works, that is explained here. The metal detector works on the principle of resonance in AC circuit. When you walk through a metal detector, you are in fact walking through the coil of many tons. The coil is connected to a capacitor tuned so that the circuit is in resonance. When you walk through with the metal in your pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. And this change in the current is detected, and the electronic circuitry causes a sound to be emitted as an alarm. So on this particular principle of resonance, it works. Now next topic, that is LC oscillations. See, suppose we have a capacitor and inductor, and suppose capacitor and inductor are connected with each other as shown in this circuit through a key. Now initially the key is open, and at time t equal to 0, suppose the capacitor is fully charged. Now here we are considering the idealistic situation. There is no dissipation of energy in the form of heat in this particular circuit. Okay, by considering this thing, we are considering this circuit. At time t equal to 0, suppose the capacitor is fully charged, and charge on the capacitor, that is maximum one, and that is Q equal to Qm. Okay. Now we switch on the circuit. As soon as we switch on the circuit, then charge will flow in the circuit, capacitor start discharging, and current will be constituted in the circuit. Suppose at a particular instant t, charge on the capacitor is Q and current in the circuit, that is I. So potential difference across two plates of the capacitor, that is Q by C. Potential difference across inductor, that is minus L di by dt. So we can write as per Kirchhoff's second rule, Q by C minus L di by dt, that is equal to 0. So here we have I, that is dq by dt, but we take I, that is minus dq by dt, because here with time the charge is decreasing one. Clear? So rate of change of charge, that is decreasing one. Therefore here we introduce one negative sign. So now if I is replaced by minus dq by dt, then we will get the equation L d2q by dt2 plus q by c, that is equal to 0. Okay. Now we can rewrite this equation as d2q by dt2 plus 1 upon lc into q, that is equal to 0. Now see, the form of this differential equation is exactly like the differential equation of pure simple harmonic motion, means intrinsic oscillations, that is d2x by dt2 plus omega 0 square x equal to 0. Now by comparing these two equations, we can say this constant omega 0 square, that is 1 upon LC. Now in standard 11th, when we discussed this differential equation of simple harmonic motion, we derived its solution, that is y equal to a cos omega t plus phi. So here we can consider the solution of this differential equation of charge as q equal to qm cos omega t plus phi. Now at time t equal to 0, q equal to qm, that we discussed very first, At time t equal to 0, capacitor is fully charged. So that is the maximum charge on the capacitor. So in this equation, if we substitute t equal to 0 here and q equal to qm, then we will get cos 5 that is equal to 1. So phi that is equal to 0. Now, if we substitute phi equal to 0 in the solution of the differential equation q equal to qm cos omega t plus 5, then if we substitute phi equal to 0, we will get q equal to qm cos omega 0 t. Now, I, that is the differentiation of this one, dq by dt with negative sign. So that will be I qm omega 0 sine omega 0 t. So I that is equal to Im sine omega 0 t, where Im that is qm into omega 0. Now we have the equation of charge at any time t as well as the current at any time t. Now let's think about the energy. Okay, so at any instant t, the energy in the form of electric field, that is q square by 2c, but charge at any instant, that is qm cos omega 0 t. So we can write here qm square upon 2c cos square omega t. Similarly, at the same instant, energy in the form of magnetic field, that is um equal to half li square, that is half l, I that is im sine omega t, so im square sine square omega t. Okay, now here you can write um that is half l. Now im that is qm omega 0, so qm square omega 0 square sine square omega t. Now omega 0 square, that is 1 upon LC, that we discussed on the previous page. See here, by comparing these two differential equations, we mentioned this thing omega 0 square, that is 1 upon LC. So here if we substitute 1 upon LC, then LL will be cancelled. So we will get energy in the form of magnetic field, that is qm square by 2c sine square omega t. So now resultantly we are getting energy in the form of electric field qm square by 2c cos square omega t, and in the form of magnetic field, that is qm square by 2c sine square omega t. Clear? And now with time t, here as per this equation of charge and current, see, current and charge are continuously changing with periodic functions. Means periodically charge or the current is changing. So we can say this one is the oscillatory circuit, because charge is oscillating, increasing, decreasing, increasing, decreasing, increasing, decreasing, like that. And energy also here changing continuously from electric energy to magnetic energy to electric energy. Clear? Any doubt up to this one? 0. So at time t equal to 0, we can say the total energy that is in the form of electric field and energy in the form of magnetic field, or we can say magnetic energy, that is 0. Then at time t equal to t by 4. So here if we take omega, that is 2 pi by t, and substitute t equal to t by 4, then this will turn to pi by 2. So electric energy will be 0 and magnetic energy, that will be maximum 1 qm square by 2c, or we can say that is half Lim square. Then at time t equal to capital T by 2. So again here if we substitute t equal to t by 2 by taking omega equal to 2 pi by t, you will get the total energy that is in the form of electric energy, and at that time magnetic energy will be 0. Again at 3t by 4, electric energy will be 0 and the total energy will be in the form of magnetic energy. And at time t equal to capital T, again we will get the total energy in the form of electrical energy. Okay. Now here if we take more less time interval here, t equal to 0 and t equal to t by 4. Suppose here we consider t equal to t by 8. So if we substitute here small t, that is t by 8, 2 pi by t. So we will get here this one pi by 4 and cos square pi by 4, that is 1 by 2. This will be also 1 by 2. So in that particular case, we will get the total energy that will be half in the form of electric energy, half in the form of magnetic energy. So in this way, the oscillations will be obtained. Here, the idealistic situation is obtained, means there is no resistance of the inductor is considered. It implies that the dissipation of energy in the form of heat, that is 0. Otherwise, in realistic, there is some resistance, and due to that the dissipation of energy in the form of heat is always there, means the total energy that will be slowly decreasing one, and finally your oscillations of charge will vanish. Clear? And suppose here we consider the idealistic situation, then also the decrease in energy takes place, because oscillating charge that emit the electromagnetic wave, and electromagnetic wave, that is nothing but energy. So oscillating charge when emit the energy in the form of electromagnetic waves, then also the energy associated with this LC oscillatory circuit decreases, right? So here always the energy decrease takes place and oscillations will be damped oscillations. See example 7.11. So that in the free oscillations of an LC circuit, the sum of the energies stored in the capacitor in the inductor is constant in time. Now see here, with this particular derivation of the energy at any instant t, the energy in the form of electric field, that is qm square by 2c cos square omega t, and at any instant t energy stored in the form of magnetic field, that is qm square by 2c sin square omega t. So now at any instant the total energy, that is ue plus um. So if we take the summation of these two, then qm square by 2c, that is common. So into bracket cos square omega t plus sin square omega t, but that is equal to 1. And therefore, the total energy that will be qm square by 2c, and that is constant 1. That is constant 1. Clear to all of you? So that particular example 7.11 is discussed with this theory of LC oscillations. Transformer. Transformer is the device with the help of which we can increase or decrease the voltage. And we know this thing, in the transmission of electrical energy, the power loss takes place. So with the help of transformer, when we increase the voltage, and then after, if the transmission is carried out at high voltage and low current, then the transmission loss that can be minimized. Now this particular device transformer works on the principle of electromagnetic induction. Now its construction. So say, suppose as shown in this figure, sometimes this type of shape of the core, which one is made by soft iron, is taken. Or sometimes this type of rectangular or square iron core is taken. And now on this particular core, two coils are wounded in such a way that each and every turn of both the coils that is insulated with respect to each other. One coil that is called primary coil, to which the input supply is given, and another coil across which the output is taken, that is called secondary coil. Okay, so here as shown in this first figure, we can take this red coil as primary and this blue coil as secondary coil. Here as shown in the second figure, we can take this left hand side coil as primary one, and on right hand side the coil is a secondary coil. The circuit symbol for transformer, that is like this as shown in this figure. Clear? Now suppose number of turns in the primary coil, that is Np, and number of turns in secondary coil, that is Ns. Now if supply is given to this primary coil, means some current is passed through this primary coil, then the flux associated with this primary coil, that we can take total number of turns Np, and suppose the flux associated with each turn, that is phi, then we can write the total flux associated with this primary coil, that is Np into phi. But now if the supply given to this one is continuously changing, means AC supply, then flux associated with this primary coil, that is also changing one. So here across primary coil, the EMF, that is minus Np d phi by dt, that is also represented as Vp. Now when the current is flowing through this primary, the magnetic field is produced, and those magnetic field lines passes through these primary coils, but primary coil is wounded on the core of soft iron, and soft iron attracts the magnetic field lines, and therefore maximum magnetic field lines will pass through this one. But see, the same core is here for secondary also. So when those magnetic field lines are passing through this particular core, it implies that that magnetic field is passing through this secondary coil also. So here if the flux is changing associated with primary coil, then flux will change associated with secondary coil also, and therefore across two terminal of the secondary coil, the EMF obtained, that is ES, that is minus NS d phi by dt. Here NS, that is the number of turns associated with this secondary coil or in the secondary coil, that is also represented as Vs. So now from these equations we can write, if we take the ratio of these two, then Vs by Vp, that is Ns by Np, or we can write Vs equal to Vp into Ns by Np. Now see here, suppose input voltage here, that is 100, Vp is 100. And now number of turns in secondary is 100 turns and number of turns in primary, that is 10. So 100 by 10 here if we substitute, then 100 into 100 by 10, so you will get resultant Vs, that is 1000 volt. Means input voltage given, that is 100 volt, and output voltage obtained, that is 1000 volt. And means here we can say if ns by np is greater than 1, then output voltage will be greater than input voltage. એટલે આપણે ઇનપુટમાં જે વોલ્ટેજ આપ્યા એને ટ્રાન્સફોર્મરે આઉટપુટમાં મોટા બનાવીને આપ્યા આપણને. એટલે આ ટાઈપનું જે ટ્રાન્સફોર્મર હોય, that is called step up transformer. And the transformer for which ns by np is less than 1, so in that particular case, the output voltage that will be less than input voltage. So that is called step down transformer. Now, if we think about the ideal transformer, then for ideal transformer, input energy that is equal to output energy. So input energy, so input supply Vp, input current Ip, then we can write Vp Ip. That is equal to output voltage Vs. Suppose output current is Is, then that is Vs Is. So Vs by Vp, that is Ip by Is, that is Ns by Np. Means here you can understand if voltage in output increases, then current decreases, but the power that remains the same. Power that remains same one. Clear to all of you? Any doubt in this one? Idealistic situation. Now in idealistic situation means for ideal transformer, input energy that is equal to output energy, or we can say input power that is equal to output power. But in practice, always there is the dissipation of energy in the form of heat. Okay. And now in different ways the energy loss takes place in transformer. Say in practice, what happens? The energy loss occurs due to different reasons. For one, that is a flux leakage. So here there is always some flux leakage, that is not all of the flux due to primary passes through the secondary. Due to poor design of the core or the air gap in the core, it can be reduced by winding the primary and secondary coil one over the other. So this one design is good compared to this one. Then second thing, resistance of the windings. The wire used for the winding has some resistance, and so energy is lost due to heat produced in the wire I square R. In high current, low voltage windings, these are minimized by using thick wire. So for these windings, some resistance is there. And in third chapter, we studied this thing, resistance R, that is rho L by A. So if cross-sectional area of the wire is more, means for thick wire, the resistance is less. So now we have to use thick wires for the winding of the transformer. Then eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by having a laminated cores. So this core part, which one is made by soft iron, right? That we have to use in the form of very thin laminated plates, and by joining them we have to make this thick core part. Okay, so the effect of eddy currents can be reduced. Then after hysteresis, so the magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to a minimum by using a magnetic material which has a low hysteresis loss. So here, when the current is continuously changing directions, positive, negative, positive, negative, positive, negative, half cycles are appearing at a terminal of primary. So when current is continuously changing its direction, then magnetic field produced in this one is also continuously changing one. And therefore, the magnetization and demagnetization of the core part take place. So for that, hysteresis loop will be formed. And now, and in the magnetization and demagnetization of the substance, we already discussed this hysteresis loop, and we discussed this thing. The area of the hysteresis loop give you the loss of energy in the form of heat. So here, as a core of this transformer, we have to use such a material for which the hysteresis loss is minimum. So now using these transformers, the long distance transmission is carried out. So when we transmit the energy at that time, we use step up transformer, which increase the voltage and decrease the current. And when the electrical energy reaches to the end user, then step down transformer will give you the original form of electrical energy, means it will give you the required voltage and required current to the end user. To minimize this transmission loss, this one is very, very, very useful. So now the chapter is complete.